Hi, this is Masa and I'm going to present Ekman Motion, which was a week 5 content. For simplicity, we look at the two-dimensional case first. When the wind with velocity of UA is blowing at certain height above ocean, the surface stress is exerted at the surface of the ocean, which is represented by tau equals to density of air, rho, times the drag coefficient, CD, times the wind velocity squared, UA squared. This has the unit of force per area, and this is the same as pressure. Due to the friction between the wind and the surface of the ocean, the top layer of the ocean moves along. This triggers the layer below to move with slower velocity, and this repetition continues until a certain depth, where there is no influence of the force, and we call this depth Ekman depth. Also, we consider shear stress acting inside the ocean, and this is a shear stress acting on layer to the other inside the ocean, and this is proportional to the velocity gradient. This is represented by tau z equals to mu times du by dz, where z represents the depth of the ocean, so as the z increases, the deeper it gets. Mu represents viscosity, and u represents the velocity of the ocean layer, and this is not the same as the velocity of the wind. And also, the horizontal force per unit mass is represented as follows. This is basically considered as derivative of the shear stress inside the ocean. In 3 dimensions, we see that forces on the layers are at different angles, forming a spiral shape known as Ekman spiral. We know it had spiral shape from the derivation from the 2 equations at the top. These equations represent the balance between Coriolis acceleration and the horizontal force per unit mass. These 2 equations has a general solution, which is represented by S of z, and this is a velocity vector equation. Note that this is a complex. And from this general solution, we know that Ekman layer depth is represented by square root of 2 nu of f, where nu being kinematic viscosity and f being a Coriolis parameter. And we find the average motion of this Ekman spiral by integrating from 0 to infinity, which is the same as integrating from the surface of the ocean to the Ekman depth, basically. And by calculating, we found that this is equal to tau over f rho times e to the minus I pi over 2, and this e to I pi over 2 meaning 90 degrees, and therefore we find that the average motion of the Ekman layer is equal to the right direction of the direction of the wind. And this in the northern hemisphere case, this is clockwise, and this is opposite in southern hemisphere. And now I talk just a little story about how this Ekman spiral, Ekman motion was discovered. Going back to 1890s, Norwegian explorer Fridtjof Nansen had an expedition aiming to reach North Pole. And this was held between 1893 to 1896, 3 years. And on the way, he observed ice drifting at an angle of 20 to 40 degrees to the right of the prevailing wind direction. And this is the first observation of this Ekman motion. And later, someone called Ekman formalized and found that it has a spiral shape. And actually, when we look at the general solution used in 2 slides before, we know that S0 representing the surface of the ocean has the component e to the minus I pi over 4, and this is basically 45 degrees to the wind, and therefore we see some consistency with this Nansen's observation with the Ekman equation. And finally, here's an example of phenomena caused by Ekman transport. The accumulation of fresh water in beautiful Jaya is one of the geostrophic currents we see today. The wind and looking at the diagram on the left, the wind represented by a yellow arrow exert force on the ocean, causing Ekman transport towards the center of the Jaya, causing the rise of the sea level at the center of the gyre. And that is it. Thank you so much for listening.